Okay, welcome back everyone. So we will begin lecture 18 today. Those of you who are online, can you hear me? Okay, thank you, Mason. All right, so we are continuing our discussion of reinforcement learning, and today I decided to talk about classical Q-learning and the deep Q-learning model, which is so that's the most commonly used model, which is like the DQN for short. So we'll try to understand what exactly this Q-learning is and how is it applied to problems, specifically to problems that are grid-based, right? So we'll try to understand that. And then we'll move on to something that's known as like the Q network. And finally, we'll try to understand something that's known as your experience replay, right? So of course, I'm going to give you a high-level idea of each of these with respect to the equations that we derived earlier, like how does the value play a role, how does the Q value plays a role. And so let's begin with the classical Q learning. And it's important to understand classical Q learning because eventually the deep network that's built off of like this classical Q learning is based on the same ideas. Okay? So what is Q learning, also known as quality learning? It's a model-free reinforcement learning algorithm, meaning we don't have a specific model for my environment. Okay, so I'm just interested in a particular state, and more specifically, I'm interested in some observations. So I don't try to model the entire environment because obviously that's in many complex situations that's like very difficult to do. And so we see that like the moment we bring in neural networks, that becomes easy because neural networks are able to, based on similarity, are able to estimate a lot of things, and we don't need to model the entire environment. But now we are looking at the classical Q learning, and the approach stays the same. We have this model-free kind of an environment where we are trying to learn based on my agent's actions and the states that the environment is returned. Okay, so Q learning, in short, is an algorithm that finds an optimal policy in the sense of maximizing the expected value of the total reward over multiple time steps, right? So basically, just remember that we are trying to maximize that Q value that you've seen before, okay? So let me just quickly remind you what reinforcement learning is before we jump into this frozen lake example. Okay, so remember we have like this closed form where you have the agent, right? And then you have the environment, right? And the agent interacts with the environment. So the agent interacts by taking some actions, right? Let's say time step T. And then the environment like gives back some observation, which is known as a state. So maybe T plus 1. And then the reward that the agent gets, right? So that's the closed loop process that we talked about last time. And the intuition of this Q learning is that if my environment is having like discrete states, right? Then what I can do is I can come up with, okay, let me just pause. People who are just coming in, you can take candies. I got them like Halloween candies. And people who are online, I'm sorry, you're not getting the reward because we're talking about reinforcement learning. But yeah, just to let you know, if you ever come to the Amos Eaton building, I asked Cheyenne to put like some candies there as well in Amos Eaton 118. So you can pick them from there. Okay. So coming back to our discussion of Q learning, so like the intuition of Q learning is the same, that we are trying to model this relationship between agent and environment in a discrete setup, meaning that I'll have some discrete states and I'll have some discrete actions. And in some ways, I can keep track of all these discrete states and all these discrete actions. And then I can come up with like the state space, which will be discrete. And then my agent can, based on those actions or like based on whether it got a reward or not, it can continue to learn. So that's the high level idea. And so let's look at this frozen lake game to better understand how Q learning works. Okay, so this is a very well documented game. Whenever we talk about reinforcement learning, we talk about this because this is like the simplest possible game that you can think of. So let's look at this. Let's try to understand what's happening. So I have this agent here. That's you or me, right? And we can walk on this frozen lake. And we can take certain actions. For example, I can go towards the right, I can go down, I can go left, and I can go up, right? So I have like 4 possible actions, right? And notice these gray boxes, right? So on these gray boxes, this is like a thick layer of ice, so the agent can walk on them. And the goal is to get this frisbee eventually, okay? So my agent can walk over all these gray squares, but the moment it steps on like this, these blue squares, that's a hole and you fall there and then the game is over, right? So it's as simple as that. So there are certain set of actions, right? And then there are certain set of states. So what exactly is a state? Because this is such a simple like example, let's say my agent is standing here at position 0, 0. So that is a state. Let's say my agent is at position 0, 1, then that is a state. So the state is the entire environment, like my entire board. For example, like to better understand that, let's say there's a game of chess going on. So like, let's say I make a move and then the opponent makes a move. Each of our moves are just observations. The entire board, the entire configuration of the board is my state. Okay, so like it's easy in this one because like how does the state change? It just changes by like one position, the agent moving like one position. That's all that's happening here. All right, so basically I have some, this is a 4x4 grid. So I have limited possible states, I have limited possible actions. So I can come up with a tabular way of like capturing all the states and all the actions, right? I can come up with certain tables that will capture all possible actions and all possible states, right? So one way of doing that, and that's known as the QLearning table, is like we create a matrix which is considered to be the brain of the agent. So every time the agent plays, whether it loses or it wins, right? Those are the only 2 outcomes. So every outcome is considered to be your reward or your penalty, like whichever way you're trying to model this, right? So let's say like in my very first run, which is also known as an episode, I think we talked about it in like the first lecture, right? So in the first episode, let's say my agent loses, and it can lose over like 100 episodes, but that is fine. I'll have like values in my Q table populated according to that, because eventually I'm getting the Q value that we derived last time, and the Q value depends on like how much reward you're getting or you're not getting, or maybe you're getting a negative reward, right? So let me show you how this table looks like. So basically I'll have like action uh, right, like I can move right, right? Action left, action up and down, right? So all 4 actions. And then I can have states here. So I'll begin with state 0, right? And state 0 is like when I'm just starting. So that's state 0. I can like name it anything. Basically, again, it's the entire configuration of the board, and it's up to you how many variables you're trying to capture, right? But in this game, it's just like the position of the agent, right? And then state 1, state 2, and so on up to state 15. Because there are like 16 possibilities of like where my agent can be. That's why I have like 16 states. So basically I have some limited actions available. I have some limited states available. So I can have this like entire configuration that's here. And like, how do we fill this now? That's the important question, right? How do we start filling this table? And like the way we fill it is something that's known as the Q function. We talked about it last time. So I wouldn't go into the details or the math behind it just yet. Just a quick reminder, what the Q table was telling us what is the expected reward, the long-term reward that my agent is going to get by being at, like by taking certain action under a certain policy, right? So if you remember, my Q was like a function of S and A. So S is like I'm currently in this state. If I take action A, this is the expected reward I'm going to get. And that also included the long-term reward. Right? So I'm going to fill this up with these Q values, right? And then based on this Q values, my agent is going to move, like is going to take an action depending on like whichever is the max Q value that it's getting, right? So there is a nice article that actually gives us the exact, I think I had that. Before we move on to the Yeah, so basically how this works, like this QLearning table is filled, is that I'll randomly initialize it to 0, right? Because like there are no Q values there. Now my agent will take randomly any steps. It might get a reward or might not get a reward. And by reward, I mean that if it wins, then only I'm going to update my Q table. So my Q table does not get updated by like every single movement in this one, right? So every single movement is not going to update my Q table. I will like eventually see, let's say my agent falls in one of these blue boxes, then the agent does not get a reward. Or maybe the way I modeled it, the agent gets a penalty. Right? And so that's what's going to decide my expected reward or expected penalty. Now, if you remember, we derived this Q equation and how to like compute the Q value. And I'm going to show you just that here. So here, so they're not looking at this frozen lake example. They're looking at a different example. But regardless, if you remember, this was my Q value. Right? So this was my Q value, and I think I had it here as well. Because now the question comes up, like, how do we train this model? I know that like I'll be filling it up with Q values, but how exactly, right? Now we consider like every action that is being performed by the agent is in some time steps, right? So time step t plus 1, and let's say my time steps are my episodes. So in the first episode, it's time step t. In the second episode, it's t plus 1, and so on. Okay, so that's the first thing. And then, if I remember correctly, and then this is the update equation that's going to happen. So let's actually dig deeper into what these values are. So if you look at this like QSA, this is the one that we derived last time. And what exactly is happening? So, like how exactly is the update happening, and how will you actually like program this is something like this, right? So actually this is not the right way of writing it. Plus this alpha is a learning parameter. Plus this value, just notice this value, this is my R plus gamma. Remember the discount factor. So R is the immediate reward that I'm going to get in state S, which is the complete run of my agent in one episode, right? And then this is the maximum that I can get, the maximum reward that I can get over like, and this is the expected value. So remember we were talking about probabilities, we were talking about the probability of policies. So that is like computed from there. Right? So this part here can be thought of as like the maximum that you can get over like subsequent time steps, right? And this again is my like the current state Q value. So high level, what's going on in this like training process as my agent like learns through this, like moving from like going from start to the end again and again, maybe like over 100 episodes, right? Is that I have this QSA, which is maybe like a better way to write this is something like this. So my Q new is going to be Q current plus some error term. Now this is important. If you just look at this part here, this is some error term that I am like through this learning process getting. This was my initial Q value, right? So Q value basically the reward that you're getting by following this policy in state S versus like some expected reward that you might get and the maximum that you can get by taking some action, right? And so the difference between them is the error. And the moment you get that error, that like the difference between the target and the, because my target is to maximize this Q value, right? So this is my target and this is my current in some ways, right? So my Q new, my new Q value will be in some ways like a sum of whatever I have in current. And then the target, that's the maximum that I can get, the best I can do based on like my expectation equation minus my current. Right? And so this is the thing that drives my entire update process, this like Q calculation. So this Q calculation should happen in every time step T. In my frozen lake example, I'm defining my T as my entire episode. It's totally up to us, like how do we model this environment? How do I define my T? Right? So I have defined my T as being like the entire episode. So what exactly we are doing? We are mapping actions and states via my Q function. right? Because my agent is moving and getting some reward or not, or maybe getting a penalty. And after some training process, I will have my Q value filled up in my table, right? I'll have a Q value for for those boxes in my frozen lake or my grid, right? A grid-based problem. I'll have all the Q values filled up. And then I might go and look for, like, it would be more like a lookup table. And I can look for, like, how am I going to get the highest reward, right? So it has, like, this is a mathematical proof that you'll find in a lot of papers. It has been proven that discrete actions and state spaces actually converge under this approach. They do converge because this error term in every subsequent episode goes down, because that's what you're trying to do here. Okay, so all of that is good. And let me go back to that example that I was showing you. So you can, like, go and read this, how this Q update happens. So that's the same equation that we derived last time. And this is how, like, the Q table is initialized to 0. After a few updates, Q table will have some values. And then eventually we'll have, like, the Q values filled up. And so the issue that comes up here is that, let's say I have, like, the Q table filled up with some values, with some numeric values. And obviously I'll have some path that will have, like, very high Q values, telling me that this is the path for my reward, right? So then obviously if I have a Q table filled up, next time I'm running the same example, or let's say I'm, like, playing this game Frozen Lake again, my agent will just pick that up, right? I mean, it already has, let's say it has figured all the Q values. So that's the maximum expected reward path, right? And so it's just going to pick that up again and again. So where exactly is the generalization in this? So there isn't, right? Because I just, like, let's say I did the entire update process again and again, maybe in 1,000 times. I found, like, one path that leads me to this, like, winning position. And already I have the Q values filled up for every episode until I got the reward. And so I know that this, like, greedy approach to just picking up the same path will lead to me winning again and again. But because this is like a machine learning problem, and we train our agent, or we train our model so that it can generalize, right? So next time when I come up with the same problem, and let's say I move a few things here and there, let's say I move this hole here, again, my agent should have, of course, it should utilize the Q values, but it should in some ways be able to find a new path as well. That was the whole point, right? And so that, like, with the basic approach that I just told you, that is not possible, right? So we'll have to do something extra to that, right? Because here I just said keep running it randomly, keep calculating the Q values, and eventually when they converge, that means you're like, you find the goal, then just stop and keep the Q values in the table. So, well, there's something that's known as exploitation versus exploration. And we talked about it in the very first lecture, which is an important part of, but I would say this is like another way of saying approximation versus generalization in reinforcement learning. Okay. So as I said, as the agent begins to learn, we want it to take some random actions as well. We don't want it to just go and pick the maximum Q value all the time, like, believe it or not, right? Because the whole process we did so that we can get the maximum Q values for every, like, path, and then just, like, pick those up and pick those actions basically that led to my maximum reward. That's what I said just now, right? But as I said, like, as the agent starts to get better with more and more episodes, my Q function will like, converge to more consistent Q values, meaning I will start getting the same Q values over a period of time. So I need to stop that somehow, because that's not good for generalization, right? Because we want it to be ready for any configuration of the same grid, right? So for that, we do some kind of a balance between exploration and exploitation. First, let's understand what is exploitation. So exploitation is, my agent learned that this is a good path, right? This, like, going right, and then 4 times going down, and then 1 times right? And it got a reward. So then I have that value in my Q table, and that was giving me the max reward, right? So I can just exploit that again and again. because my agent just realized that that's the path for maximum reward, right? So I can just like keep my agent moving in the same direction. And that, by the way, applies to any other game in like general, right? If you know that this is the path to winning and nothing changes, let's say your states don't change, just like let the agent keep following that path. Like, what's wrong in it, right? But that's not quite like what we want, because of course this is a greedy approach, and that can lead to getting higher rewards, because I already know I'm going to get a reward by following this path, right? But I want some level of exploration as well. So I want to introduce some level of randomness in my implementation. And reason being, because maybe there was another path that wasn't explored as much. So I want my agent, despite getting like good Q values, to go and pick those random paths as well. So like in case of this frozen lake example, so let's say I have like my grid filled up with Q values, right? And this is my state action table, let's say. And let's say I'm in this, like my agent was somewhere here. And the actions that like the Q values are the max for this action number 2, maybe, right? But when I'm in state some ST here, right, I'm seeing that action number 2 is the best because that has the highest value, and these have like some 0.05 or 0.00. They don't even have anything, right? However, I want it to move somewhere in this row, and this is like my state action Q table, right? So what I do is I explicitly go and let the agent like deviate from this 0.1 and maybe randomly select either this or this in the same row, because I am in the same state, obviously. But in that state, I wanted to select like maybe 0.05 or maybe this 0 value, because maybe that will lead me to a better path or a faster path or an unexplored path, but it would still lead me to winning, right? So in order to balance both of these, there is something that's known as the epsilon value that we introduce in every QLearning, especially like both with classical QLearning and deep QLearning, we introduce something that's known as epsilon. So epsilon is something that's like a value between 0 and 1, right? So you can say that the agent can take some action, some random action with probability epsilon, and it should take a well-defined Q action, that was my greedy action, with 1 minus epsilon probability. So basically, if let's say epsilon was 0.2, then there is a probability of 0.2 of my agent picking a random action, so picking anything else in that row, and there is a 0.8 probability that it's going to pick the best Q value. So we keep that approach there so that it learns as well as it generalizes. Right, so think of epsilon as some like decaying value, because the decay of epsilon is a strategy that will impact the overall learning process. If you keep the epsilons small, that means there are less chances of picking the random value, right? The random path. And if you keep it, so obviously it will take more time. The entire learning process will take more time. And if the epsilon value is big, it is like it has a greater probability or higher chances of picking the greedy approach, and so it converges faster because we've already looked at the greedy approach being like the winner. Okay, so for example, that's what I think I already talked about this. We can either choose the action for the maximum Q value, or we can choose any other action in that particular like state. And this happens time to time. So you don't have to do that all the time. You can just like configure that, like when or with like what, how many, after how many iterations do you want it to do that, right? And so this tendency will like create a balance between the random choices and the greedy choice. Okay. So overall, this mechanism helps to learn instead of stopping after the very first time, because if you think about it, the very first time I let my agent win, I got the Q values in my Q table, and that's it. My agent will always win that game. But I don't want it to just like stop there. Okay, so going back to the Q value that I just like talked about, here this actually gives us a demo of how you can calculate for every state, how you can calculate the Q values. And it's just like substituting these values in your Q equation that we derived last time. The only difference here is that this is given for another some car movement, grid based, like again, it's a grid world. But yeah, you can do the same thing for your frozen lake example as well. So just like go over this, how exactly they're plugging in the Q values and how they're filling in the table. That would be a good exercise. And another thing, like we have our state action table flipped. So that's the only thing different here. So just go over how they are like, and they obviously they have demonstrated for a few values, not all the Q values. So you can just like go and check for our frozen lake example, but it shouldn't be that hard. Okay, so I think I talked about exploration and exploitation. And here is the entire like pseudo code for how you can use QLearning with like this tabular data and how you apply like epsilon and let it learn. Okay. So that was classical QLearning. It was for discrete environments. So why discrete? Because I can actually come up with like all possible states and all possible actions in a single table, right? But then there are some issues with this, like even like for example, for a game like tic-tac-toe, and I'm sure like everybody's familiar with that, right? So there are ways, and like if you just like go and Google tic-tac-toe or reinforcement learning, you'll see even for that, there is a well-defined state space and action space. So people have come up with like all possibilities that can happen. And again, going back to what state is, state means like the entire configuration of the board. Now think about chess. So the game of chess is more complex. And as I said, there could be so many configurations, right? So if you think about the state space, although that's also a grid world, right? It's also a grid-based game. But there could be so many states. And believe it or not, that problem is still unsolved. I think you can just like go and check. The number of configurations that have been approximated, so it's like 10 to the 43 to 10 to the 47 or something, like that range is there. But we don't know for sure how many configurations exist for the game of chess. And although it's a grid-based game, right? So in some ways, this is telling us that keeping a track, like what I did with the frozen lake, I said, I'm going to calculate all Q values. I'll keep running until I get all Q values, and then I'm going to like proceed from there. It's somehow not practical for like every problem. And then if we think about like self-driving cars, for example, right? That they have a more continuous type environment. It's not that they're moving in a grid and they have like only these set of actions possible. There are so many, like there is this entire, as we talked about last time, right? There's this entire space of actions that's available. So basically the motivation behind DQN or deep Q learning is that, right? So we want to focus on a policy that uses neural networks. And the fundamental, I would say, motivation is the tabular form of describing a policy is not scalable. Like if the table becomes big, like think for the game of chess. And remember, the state action is not the picture of chess board itself. It's all the states that are possible and all the actions that are possible. So my action table will just blow up, right? It's going to be huge. So that's why like tabular form of describing a policy is not scalable, because like what is Q? If you remember the definition of Q, it's like what actions to take under this policy when in state S, right? So that's what we are trying to learn eventually. And most real world problems are continuous. So this tabular approach doesn't look good. And as I said, large tables will lead to complex mappings, and the agent will have to visit all states to update the policy. So that's another thing I think maybe I forgot to mention, that in order to update because the Q actually, the Q update is my policy update in some ways, right? Based on like what reward I'm going to get when my agent is at this position. So what we want for the entire Q table to be filled, we want our agent to have visited like every position, right? Every state basically, because every position is the state in my frozen lake example. And that's why we look at the frozen lake example, because it's so simple. But then it's so like, think about the chessboard itself, like one piece, any piece, we need it to visit like all possible configurations that are possible for that piece. So that's like, I don't think that's practical, right? So what we do is we use neural networks, because let's say my agent does not need to visit all possible states in my problem, in my environment. And my neural network can estimate values for the states that my agent has not visited. And it can do policy updates based on that, or my Q value updates based on that. Okay, so that's the fundamental idea, that my neural network has a power to estimate things based on the similarity of some observations that it has seen. and and the current state, and then it can like make those estimations, and then I can like keep doing that, and I can learn this environment, and maybe my agent does not visit that state, but I have some Q value for that state if at all it visits. Okay, so what we'll do is we'll begin with like a quick reminder of the Bellman equation, because we will look at the value and policy network. So the way this like deep Q learning works, and by deep Q learning, I mean only Q networks. So I'm not going to go into any other topics because I know that's like a lot. There's a lot out there. So I don't want to like go into every minute detail of everything that's there. So that's why I will just focus on Q networks, because these are the most common ones. And if you understand this, most likely the others would be easy for you. So this Q network is based off of like two networks. The first one is the value network. And then the second one is the policy network. And of course, their names will eventually change as we'll see the way they are implemented now. But for now, just like think of these as value network and policy network. So what is this value network? A value network is something that's based on the Bellman equation of value. So remember, we were finding the value of a particular state by being in a particular state, the value that the agent will derive by being in a particular state. And this Bellman equation was given by the max of taking action A, immediate reward, plus the discount factor, Vs prime. Right? This was my Bellman equation. And I'll see why this is important. And the other thing that I need to remember, and maybe we can talk about that later. Okay, I think we can talk about that later. So first, let's try to and remember this is the Bellman equation to compute value, right? And my neural network can estimate, as I said, can estimate values or policies for states that the agent has not visited. So maybe in some ways, like if I think about my grid example, right, my frozen lake example, what I'm saying is, let's say my agent is somewhere here, in some position here, right? And because based on the input of this position, whatever this is in my grid, let's say it has some value, this position has some value, I can estimate the value of like this position because it's like one position ahead of this one, and maybe like this position, maybe this or this, depending on how my configuration of my neural network is. Of course, I'm not saying I'll get the exact value, but I can estimate, right? So this is the idea that's applied to the entire Q network. So let me show you what's going on here. So for example, and I think I'm running out of space, so I'll do that again. Let's say I have a very simple neural network, and in my grid, I have some position, which is like XY coordinates. And of course, you can have other observations as well. So one thing we need to remember is that there is something that's known as a state, and then there's something that's known as an observation, right? I think I talked about it in the first lecture, but to quickly give you a difference between the two, state, remember, is the entire configuration of my board, but my observation is where my agent is currently, or something like that, right? A very specific thing that I'm interested in, right? So let's say this, my XY is my observation, and a neural network is okay with the observation to just compute the value. It doesn't need the entire state or description. So for example, I can create a network where I can input like my X and Y values of my agent. And let's say I have like a 4 layer network, and it's fully connected. And then eventually I can, out of this network, I can get some value V. Right? So the whole idea is that we can get the value calculations using these neural networks. That's the first point. And if like two states are similar, then their values can be considered to be similar, and then similarity can be decided by the neural network based on the observation inputs, right? So the value this neural network can take, it can take observations from states that were never seen before and still predict something. So that's the idea. So the first network that we have is the value network, where we have like some input observations, and this value network gives out some value for this particular, the estimated value for this particular state, or this particular observation rather. So that's the first thing. And we'll see how they come together and how they are helping me in computing my Q values. All of that will come later, but let's just like understand why like this is so useful. So first of all, like this is also in some ways similar to the idea, because I'm just saying that let's say I get another XY, which let's say in this case was 2, 1, right? So I'll just input 2 and 1. But next time when in my neural network with whatever weights I've learned, right? Let's say 3, 1 comes in. So based on like my previous weights, I have some information of like what 2, 1 was. And my weight updates will be based on that. Right. So that's why we are like playing the similarity thing here. And this is also like the motivation is from how humans interact with situations. So we do utilize knowledge from the past and then do something. Right. So basically, if a new value, if a new like input comes in, a new XY comes in, which is like, let's say this 5 and 5, right? If the neural network was or has seen an input that was like close to this 5 and 5, then the agent doesn't need to go to 5 and 5. The agent doesn't need to visit that, but I can derive some information from like wherever the agent visited. That's the high level idea, right? Now, this is not the only thing that we need. We also need a policy network. So we need something so that like we can have a policy that will decide what actions to take, because this is just like calculating the value. Remember, the ultimate thing is my Q value, because that decides what action should I take once I'm at this position. Of course, like the value of this is this, the value of something else is something else, but I need to take action. Okay, so the second network that we're looking at, okay, let me see if I missed anything. Yeah, so this here, I just like I'm talking about the key ideas when two states. I think I already talked about this. Yeah. So why do we need two networks? So that's because like we need the second neural network because we need some ways to output policy. And in most of the practical situations, I think we talked about that again in the first lecture, that the policy is stochastic. And that goes really well with the idea of neural networks, because neural networks can output probabilities. And those probabilities could be the whole distribution of actions that you can take. For example, let me again show you this. So let's say again in a grid, if my agent is at like some position here, now I can move up, like my agent can move up, left, or down, or right, right? And all those actions are available. But maybe with a neural network in output, I can compute the probabilities of like moving up, right, down, or left, right? So if I get like, let's say I have some probability of moving here, probability of moving this, 0.4, maybe like one of them is less, and 0.5, sorry, this is 4. So the one that has the max will be the one that I'm going to choose. Right? That's the high level ideas. How do I like make use of a neural network to get these probabilities? Well, again, I'll have some observations. The simplest way to get observations is the XY coordinates in this case in a grid world. So I'll get like my X and my Y, right? And again, I'll input in like a hidden layer, depending on like whatever problem I'm solving, I can decide on the number of nodes. And then eventually I have an output layer that can output probability values, right? So basically, I'll have the probability of, let's say, moving up, probability of moving down, probability of moving left, probability of moving right. So I can construct such a network, which can give me some probabilities based on my observations, right? So if I can get those probabilities, then I can come up with a policy of like what action to take. So for example, the one with the highest probability is the action that I'll take in this case, right? So such a network, like this network is known as like my policy network. Okay, so we have discussed about the architecture of my policy network and my value network, but how do we train them? How do we update their weights and all that? That's like important. And the other question that I think is very important is how does like the action that my agent takes impacts these networks, right? So like, first of all, what is the relation of the agent feedback and these networks? Because like, remember when we described reinforcement learning, we said that the agent takes some action and that impacts my environment. And then the environment gives me some rewards and my observations, right? So how does that work? And then how do we update the weights of this network, both of them? That's also important. And what is the relationship between these two networks? Because most likely, like the way we just described the architecture, it looks like they are like working independently, which doesn't quite make sense, right? So what exactly should we do, and how should we train? Because like in supervised learning, it's pretty like obvious that you have some input data and then you have a loss function, and then you define the loss function, get the derivatives, do the back propagation. But how do we do that here? Like, what is my target? What is my output, right? So for that, we do something that's known as the Q network, and I'm going to talk about this. So I'm going to reframe this supervised learning problem, this reinforcement learning problem as a supervised learning problem. And that's how we solve these two networks, and that's how we get the probabilities and the values. Again, if you didn't like hear me correctly, that's true. We reframe this reinforcement learning problem as a supervised learning problem. And the moment we have a supervised learning problem, in some ways, we know how to do back propagation. We know how to like solve the neural network problem, right? So the first thing is like the Bellman equation that I wrote, the value equation, that is used for the value network. And so that forms the basis of your error matrix. And the values will be learned from there. Let me just like quickly show you an example, which I just made up. Hope that makes sense, but let me. Okay, so remember the first network that I talked about that was calculating the V values, right? So it was just like giving some V output. So for example, let's say I have some X and Y. My agent visited this node, XY, and then using this, I trained this network and I got a V out, right? So then based on that, let's say this was that point in the grid, and this V value came out to be, let's say 4. And so let's let that be 4. Okay. And then my neural network also estimated these values, although my agent didn't visit those, but the surrounding values are also estimated. So let's say this estimated value came out to be 6. This came out to be 2, 2, and 2, right? And then I have to back propagate somehow to learn some weights and do something with them, because this cannot be possible. Like I'm just talking about just doing some computation of V. So what like the next action that I should take is not like picking up the 6, which is the highest estimated value. Maybe it is 6, but I have to go according to like what action should I take that satisfies my Bellman equation. That's what I have to think about. Okay, so for example, let me rewrite that. Yes, is okay. Yeah, I'm sorry. Okay, so I have just like already input the values. For example, if the reward was considered to be -1, let's assume there were some values, and then there was the gamma 0.9, and then comes this here for the future. So here I'm trying to decide what value would be for like my S prime state. And I have some estimated values for all the actions that my agent can take. So most likely, remember this has to be maximized. And so I'm going to obviously pick like my step number, like the 6, and substitute that here, right? So if I substitute this here, this is just like a calculated value. I'm just calculating the Bellman equation for this, right? For this next action. So if I just calculate this by substituting 6 here, right, I will get a value of 4.4. Right? And my neural network estimated 4. So that here is the difference that I'm going to get. And so I can make my network be trained using this difference, this error, right? So how exactly will that happen? Well, I can create some kind of a supervised learning problem in the sense that I can create a data set where I have like all of these X and Y values. So X, Y values, I mean like this is X and this is Y, right? And I'll have like these V's, those are the target values, right? And then my neural network is computing some of them. Right? So this will happen like a couple of times until I get some data for this one, right? So in some ways, I will get some target values and I'll get like some target values that are computed, and then I'll get like these values as well. So basically, I will get this data set with this error metric. So let me just write down, maybe that will make more sense. So the error metric using which my algorithm is going to learn is this VS, which was computed from my Bellman equation. Sorry, this is from my neural network minus my Bellman equation. So I'll just write Bellman equation. Sometimes squared, sometimes not, depends on how we are defining our loss. Right, so this is how I will frame this as a supervised learning problem with some targets, and I'll try to minimize the difference between this 4 and like 4.4, for example, and so on. Right, so this is how I train my value network, but I'm still not done. Just like the key takeaway here is my Bellman equation is a basis for the error metric for my neural network. That's the first thing. And I've converted my entire reinforcement learning problem into a supervised learning problem for my value network only, right? So I still need to do something about my policy network because that was giving me the Q values, right? In some ways, it was giving me like what policy to follow. So what we need to do is we need to create a data set with features that are derived from the actions that my agent takes. So that's even harder, but I will try to make it like simpler with an example. Let me again create a grid example with the frozen lake one only. And okay, so let us assume that the reward for some, like that's my goal, that to get that reward +4. And my agent is somewhere here. And this is a grid, by the way. So this is my agent, and then there is another. Okay. All right. So let's say like, so there are many ways that the agent can reach this reward, right? There could be multiple paths. And the way we create a data set for this one, because again, I'm trying to frame it as a supervised learning problem. So the way we do that is we map all possible paths to the rewards that like my agent is going to get as it goes like closer, like what gain will it have as it moves closer to the reward, right? So let's say one of the paths could be that like my agent moved here and I'm just like populating it with some gains that I'm getting, like some random gains, but it could be anything depending on the problem, right? So I get a gain of like, sorry, 1, 2, 3, and eventually I reach to this +4, right? So the closer I'm coming to the goal, I'm getting like more gain out of it, right? So some metric that kind of describes that I'm closer to the goal. And then I'll have to map like this path to some data. And of course, you can have like so many paths available to you, not just this one. I'm just showing you one, but you will have so many and you'll have to pick all of them up. So let's say this is one path where my agent moved down and then left, up, right? So how will we convert it to a data set that is like in some ways able to convert to supervised learning? So well, I'll have an input data, which is my X and Y in this case, which are my observations, right? So how my X and Y is changing. And then I'll have this gain, some numeric value that describes that I'm coming closer to my reward. And then I'll have actions. So let's leave gain aside for some time. My XY, let's say this XY was 3, 2. And then it moved to 3, 3. And then 2, 3, and 1, 3. And then there was 0 gain, then 1, 2, 3. And then there were some actions corresponding to every step. So you move down, and then you move left, and up, right? So this is one data set that you created where you have this as your input, and this is your label. The actions are your label, and your input is your positions, the observations. All right. So this can be used as a basis for training your policy network. And this is just like one configuration. So like imagine you'll have so many configurations, like this agent can move to this one with so many paths. And so you will have to somehow come up with that mapping, right? And so for my policy network, this is how I convert to a supervised learning model, right? And then you might ask, like, how does this like gain value helps? Because that's also in some ways a metric of how close I am to my reward, right? So when we are training our neural network, and then in back propagation, let's say like I get some output for some probability, and that probability, like obviously in this case, I'll have 4 of them, like top, bottom, or up, down, whatever you want to call it, right and left. So this is going to be the output of my neural network. And then when you back propagate, usually this gain is utilized to kind of give the neural network a sense that, for example, there is a huge gain when I move top from this point, right? So I'll add some weight to that particular action or that probability when I'm like back propagating it. Right? So that's how gain can be used. Gain can also be used as an input. It's totally up to us. How do we like try to model it? Right? Usually it can be used as like an extra weight to that action probability, whatever probability value we get out, like, and depending on like whatever gain we got from that action, because like we'll have a probability for every action, right? So we can multiply that gain to every probability to give it some more weight, because this action at this position, like think about it like this action at this position gave a higher gain. So I would want to back propagate that more than anything else. So both can be done. It can be used as an input as well. Like it's totally up to us. But the whole point here is that we can convert it to a neural network. Basically, we just converted everything to like a supervised learning problem. So we have the value network, and then we have the policy network. And when we can determine actions using both of them, actions and values using both of them. So now what? Now what's next? Like, where does this come into picture, this part? This, like, what exactly is the Q network? So generally speaking, people talk about Q network, and that's nothing but this, sorry. Yeah, so like finally, when we put all these networks together, we want both the value network and the policy network to work together, right? And the value network is the actual like the policy network is my Q network. So as you are seeing in this picture, and I'll come to like what is this experience replay and all that, but I just wanted to show you this is the entire like DQN that we've been talking about. This is how we like everything comes together. And we'll go through each of these parts. But for the time being, just focus on this Q network and this target. Just focus on these two. So think of Q network as your policy network, and think of this target network as your value network. So we will make some tweaks to both of them and bring them together to make this learning process more powerful, better generalization, and many other things. So that's what we're going to do now. Okay. So there's something that's known as experience replay. So whenever somebody is talking about Q networks, we will eventually come down to this experience replay. And what exactly is that? So in supervised learning, how did we like try to avoid overfitting in and have better generalization? Like one of the ways of doing that was I would shuffle my data, reshuffle it, do some kind of cross-validation, and get the results again and again, right? That's one way. But now I've converted my entire problem to my supervised learning problem, right? But now also imagine what kind of problems are we solving in reinforcement learning? So usually they are like time series type problems, right? You're playing a game of Atari, let's say, right? So my state at step t is in some ways related to my state at t plus 1. And then my state at t plus 1 is in some ways related to t plus 2, like and for that matter, any video game or any such game, or like even the game of chess. I cannot just like pick random states, right? That let's say I picked up the state at like when we started the game, and then the state when we were ending, and I just like skipped the entire like whatever happened in between. So that sequence need to be maintained, right? And by converting, like, because now I have my supervised learning problem, right? So I need my data to be like shuffled in some ways, but not quite. Like I need to maintain that context for some period of time, at least, right? So like one way of thinking about it, and another thing is like my gradient descent. If you think about like gradient descent or any other optimization problem, that in some ways has this assumption that my data is independent and identically distributed, right? It's not sequential. And remember, for sequential data types, we came up with different types of networks. So we'll have to do something of that sort here as well. So here in experience replay, we don't quite create a recurrent neural network, but rather we create this experience buffer, sometimes called as an experience replay buffer. So high level, what happens in that, and let me just like make this picture a little smaller so that we are able to visualize. Okay, this I think is okay. Okay, so this here is my environment, which is also known as experience. So that's where the name comes in. Now, experience is described in terms of your state, your action, your reward, and then the next action, which is S prime. So this tuple defines your environment. Okay. So what you can do is like you can use an experience replay buffer, which is here. This acts like a buffer, right? To sample your agent feedback from this experience. So this is like your agent's feedback that you're getting, right? And then you can mimic a data set that is in fact IID, that is independent identically distributed, not exactly, but it mimics that in some way. Okay. And then you can use a separate target neural network that should be updated periodically, not like for every target value. Because like if we think about any gameplay, let's say we're playing some video game, right? So what happens is that let's say you have some state S1, right? And then you have like some state S2. And there are like multiple states that are interrelated to one another, right? Because I'm in this state S2 because I was in state S1 and so on, right? So we want to maintain that, but we don't want to like, we also want to do supervised learning. So what should be my target? So my target could be a combination of the outcomes of all of these in some ways. And that's what's maintained here. That's that target is, and so now we are coming to something that's known as a Q network. And remember in our policy network, I was giving you the outputs as the P values, the probability values. So just imagine instead of the probability values, you have some output as the Q values, right? The idea stays the same, but you have the output as the Q values. Just remember that. And then we come to this like replay buffer. So what exactly is this doing? You must be familiar with the DQ data structure, right? So that's what this does. This kind of has like, let's say it takes agent feedback for maybe n equals 1000. So we will maintain these 1000 states. So for example, S1 to S1000 in this, right? And feed that to my Q network to get some Q value. But I will keep like a fixed target for all these because it's more like my target is continuously like might change for many of these, right? So that's like a high level idea that I have like a so again, let me repeat it. I have a replay buffer. I would just like keep 1000 values. Once that is filled, I will like give that in I don't know how to say that. So the newer values will come in and I'll just discard the previous values. But I will have some information of that in my Q network because my Q network would have learned on the previous 1000 values. So my weights and everything would be there, right? So how does this help? Well, the way, like the first thing is that I am able to mimic that my data is again IID in some sense, although it's not, but I'm still like maintaining some kind of like um, independent structure in the sense that like maybe this can be considered as like one single observation, right? And then you have one target value, which does not change. And then once you are done with the training of this entire network, you copy the weights of this like learned over those 1000 values, and you go here to this like, sorry, to this target network. And then you make the first update and so on, right? So the high level idea, for example, I'll give you a small example, like the Atari games, they need a buffer of size like 1 million to really give like good results. So that's there. So basically, like again, I'll repeat, my goal here is to create a neural network that can directly output Q values, right? So in order to do that, I have my Q network and my target network. The only difference between my Q network and my target network is that my Q network is directly getting like the stream of inputs, but my target is staying the same. That's remaining the same. Because think of like the supervised learning problem where I don't want like my target to continuously keep changing. Because that's something that's hard to like take care of. It's like you're chasing a target that's changing continuously. So that cannot happen. That's why we need these two different neural networks. Think of this target network as like where we store my labels in some ways, but those labels don't change for those 1000 values. And then they change for the next 1000 values. And so we are like getting this data set that's good for supervised learning. So once we have that, we know how to compute the loss, like the max possible value minus like my current like Q star, right? And then I back propagate and all of that. So maybe we don't need to go into the details of like that becomes super complex. As long as you understand why we have two networks, because we are trying to mimic an IID, right? And then how this replay buffer works, because there is some relationship between every state that's coming in, but we don't want to lose information as well. And we also want to create a supervised learning problem. Right? So that's the fundamental idea. Of course, there are more details in the references that I gave you, but like as long as you understand the high level idea, you're good. All right. So yeah, I know I've talked a lot. So any questions so far? Anything that's, I know it's like initially it is confusing, it is overwhelming, and it's a lot of information. You should go back and like reread at least once. So that will give you a better idea. And if you remember the book that I gave you last time, the link to that, that actually talks in detail about all of this. But today I just like wanted to keep it high level, concise, so that it's not too much for the first time. But you understand that this is how Q network works, because Q networks are the ones that are used like mostly when we talk about like deep reinforcement learning. All right. So I don't have any papers for you to read today, for the very fact that this in itself is like a lot. Uh, but like next time I was thinking of maybe going over some platforms that like open source platforms that actually offer an environment where you can actually create your own like reinforcement learning model. So one of them is like OpenGym AI. And then we'll also look like how we can do that in TensorFlow and Keras, I think. So I know like we're going more towards the practical side, but I think that's also important when we talk about reinforcement learning. Okay. All right. So that's all I have for today. And I know that was a lot, but yeah, I mean, just like go back and reread it. And if you have questions, you can always come back. So that's all I have for today. Yeah, and people who are in class, please feel free to pick some candies. And people who are online, I'm sorry, you must come next time. Maybe yeah, that's the reward that you missed. Yeah. Any questions? People who are